Okay, so we're going to focus today on closed pipes. And a closed pipe is basically what it kind of sounds like. So take a pipe, I'll draw like a side view of a pipe here. And a closed pipe is closed on one end. So this end would be closed. This end would be open. Okay? Now, kind of the theory of what goes on with these pipes, on one end you have to produce some noise, some type of sound. And typically, like if you play a trumpet, anyone here play trumpet? I forgot this was the untalented class. If you play like a trumpet or something, usually you purse your lips, so you produce a sound like something like that. Okay. Anyway, the point of that is when you produce this sound. Okay, so here's you're pursing your lips here. And when you produce this sound, what you're going to do is you're producing a wide range of noise, a wide range of sound. And so all these waves are going to come down the pipe like this. Okay, various types of frequencies. If you play like a reed type instrument, like I think it's a reed instrument, clarinet or a saxophone, what happens is this little reed flutters about, and that produces a little same thing, okay, a wide range of sound. Okay, so anyway, that comes through like here. When it hits the closed end, what happens to it? Okay, it reflects back. So we're going to have our waves reflecting back this way. Now when it hits the open end, actually two things happen on the open end. The obvious thing is that some waves are going to keep going. The less obvious thing is some waves are going to reflect again. So some waves will keep going through, that will be the sound that you might hear, and some waves are going to kind of reflect back. And so notice, this concept, by the way, it's hard to understand with sound. Anytime you go from kind of this confined region to the atmosphere, which is really big, you get this kind of effect that happens. With light, you notice it all the time. With light waves, you notice all the time. Like if you look, even now, if you look through the windows or through the cabinets, you can see through the cabinets, right? But what else happens? You can see the reflection off the cabinet. So with light, it's really, you see it all the time. You can see through and you can see the reflection. Same thing happens here. Light goes through and it gets reflected. So anyways, these waves are going to keep bouncing back and forth and back and forth. What's going to happen when they bounce back and forth? They will interfere with each other, yeah, and most of the waves are just going to kind of destroy each other. So they're just kind of destroy each other. Some of the waves, though, will be set up as harmonics or standing waves. They'll reach this kind of state of resonance where they produce these harmonics. So that's what we're going to look at today, is these waves that produce states of resonance. So I'll write it, some frequencies will resonate as standing waves. And so that's what we're going to look at now is, well, okay, which ones? Which ones do resonate as standing waves or as these various harmonics? So let's start with the first one. And what are we going to call the first one? The first harmonic. So let's start with the first harmonic, also known as, what else might I call this? The fundamental harmonic. Good. And this would be the easiest one to set up. Okay, so the first harmonic would be the easiest one to set up. So let's set up the first one, the first harmonic. So what we're going to do is, let's go ahead and draw our pipe. Pipe looks like this, closed pipe. So it's really difficult to show longitudinal waves. Remember, these are longitudinal waves. It's difficult to show a standing longitudinal wave. So we'll do it as a transverse. And what I'm going to do is draw the pressure waves. So So kind of the rule of thumb to think about is the pressure that's exposed to the atmosphere, the pressure that's open, is simply going to be that. It's going to be atmospheric pressure. It's going to be normal pressure. And so this will be our node, will be on the open end always, will be our node, and this is essentially the concept. The reason it's a node is it's just normal pressure. You can think of it as like 1 atm. So this would be like, I mean, if you were somewhere where there's no pressure waves at all, it would be perfect silence, right? It'd be perfectly silent. And so this is, you get this full constructive interference that occurs right here where the pressure waves are just normal, 1 atm. Now on the close end, you're going to get antinodes. So on this end, you're going to get your antinode, always on the closed end. And this is going to be either maximum pressure or minimum pressure. And it will actually oscillate between the two. So one moment it'll be max pressure, one moment it'll be minimum pressure. This one, it's easy to think of the max pressure like it's squeezed against the wall, so that produces kind of this high pressure region. But it does alternate between the two as the reflections go back and forth. So this is what your first harmonic looks like. Remember, this pipe has a length to it. So when you look at this picture, we want to do what we did yesterday, which is figure out the relationship between the length and the wavelength. So as you look at this picture, how many waves do you see? Okay, good. So think of a regular old wave to help you. And think about what you're looking at. So you're looking at from here to here, right? So you're looking at 1/4 of a wave. So we're going to say the length is equal to 1/4 of a wavelength. The length is equal to 1/4 of a wavelength. Okay, let's do the second. And actually, we don't actually refer to the second as the second. The next harmonic is actually called the third harmonic. Sometimes you'll actually see it called the second just because it's the next, so it's the second. But we usually refer to it as the third. And the reasons hopefully will become obvious to you later. So let's draw this one out. Just remember, on the open end, what are we going to put? A node. The close end, we're going to put the antinode. And then, just like we did yesterday, as you move up in harmonics, you're just going to add a node and add an antinode. So this one's going to look something like this. So here's the additional node right there. Here's the additional antinode right there. So how much of a wave do you see here? 1/2? Do you guys agree? So notice we're starting right here, okay, and where are we ending up? Right here. So how much of a wave is that? 3/4. Okay, so this would be halfway, right? At this point, that would be half plus another 1/4, so 3/4. Okay, let's do the next one. The next one's actually called the fifth. We will say that closed pipes only have odd harmonics. No even harmonics for closed pipes. Why don't you see if you can draw this in yourself? Try to follow the rules that I mentioned earlier. Okay, so take a look to see if you got it right. Remember, the open end always has the node. Open end always has the node. Close end always has the antinode. And then you just add one more as you keep moving up in harmonics. How many waves do you see here? 5 fours. So hopefully you're noticing the pattern. You're noticing why we call these odd level harmonics. Let's just do one more. We did 4 yesterday. Let's just say consistent. So go ahead and do the 7th. So just add one more node. And one more antinode. Okay, how many waves do you see? 7 fours. Good. So 1st, 3rd, 5th, 7th, 9th, 11th, etc. Just follow the same pattern. Okay, so those are the closed pipes. You should know how to draw them. You should know how to, the relationship with them. You should know how to go beyond the first 4. Okay. If I asked you for the 13th harmonic, you should be able to figure out what it looks like. In terms of problem solving, remember yesterday when I asked you to find the frequency, for example, what else did you need to know? The speed. Okay, so notice in our picture here, you don't have to worry about the speed down a string. Where's the speed? What is the speed? The speed of what? Of sound. Yeah, so this is, you're creating sound here. So this would be the actual speed of sound as it goes back and forth. So for pipe problems, for pipes, use the speed of sound. Specifically, we're going to use the speed of sound in air. Okay, anyone remember the equation for finding the speed of sound in air? 331 plus 0.6 TC. Now, 90% of the time, they're going to simply tell you it's room temperature, or if they don't say they don't give you a temperature, just assume it's room temperature. So room temperature is considered to be 20 degrees. So if you do the math here, what do you get? We did it the other day, 343. So that should be your default here. If they do not give you the speed of sound, go ahead and use 343.